All right. So let me do it again then. Like I really want my introduction to be. So today, again, if you are late, we have the great pleasure to have Pratik. Pratik Rajesh sometimes he is a grad student now at the computer department, and he was actually kernel engineer at IBM Linux Technology Center before joining UIUC. And he basically was working on the CPU team and almost know everything about Linux scheduler. We're super excited to hear he teaching us about Linux scheduler. So I would actually sitting in the front row as a student listen to what Pratik teach us. Thank you so much for giving us a guest lecture. Pratik, the stage is yours.
Thank you. And I don't know everything about the Linux scheduler, unfortunately. So, so that's a problem if you have expected that. But again, thank you for coming here and listening to me talk. So I know that you guys have already gotten a basic schedulers lecture, and you guys know what basics of scheduling is, FIFO, round robin and stuff like that. So this talk is not going to be about that, and I'm not going to be here defining what a scheduler is. It's not like, oh, no, a scheduler is chooses what to run where and all that. I'm not going to be telling you that. I'm going to be talking a little bit about the goals of a scheduler, and basically okay, that doesn't work. Okay. Okay, there we go. No, sorry. Okay, now it works. Cool. So basically, I'll be talking a little bit about, when I say introduction, I'll be talking about the goals of a scheduler. And there can be multiple varied goals of a scheduler, and and how is it difficult to balance between these goals. I'll be giving you a little bit of an overview of modern scheduling. So this will include a history of schedulers. We'll talk about the OFN scheduler from Linux 2.4, and then OF1 scheduler, and then and basically just about how scheduling kind of progressed through time. We'll talk about the CFS scheduler, which is also the more modern scheduler, while also talking about the other aspects of the scheduler, not just the CFS. We'll talk about beyond fairness, beyond the CFS scheduler, but I want to keep this under wraps just for a little bit more time, and I'll get to it when we actually get to this section. And lastly, the most boring section will be talking about my research around what I'm doing towards scheduling, and it's called Cat Cloud, and we will be looking for better names for this project eventually.
Most exciting one.
So let's get started. So since I'm taking a class, so whom among you can tell me, what could be the goals of a scheduler? Yeah. Mm-hmm. Yeah, that's absolutely right. So you said that a scheduler's job is to schedule efficiently, right? That's one of the things that you kind of mentioned. So, but apart from how do you define these efficiency goals? What do you say that, okay, this is what my scheduler must do, or these are the properties my scheduler must have that would make it a good scheduler? Anybody? Yeah, go ahead. Yeah, interactivity that's good. How do we decide what kind of tasks to run, whether it's an interactive task, whether it's a CPU bound task, what kind of a task is it? That's great. Yeah. A task throughput, perfect. Yeah, throughput is a very important aspect of a scheduler. If you have a lower throughput scheduler, nobody wants to use it. Anybody else? Yes. Fairness, perfect. And fairness is a big question also. How fair should the scheduler be? Should the scheduler be a little bit unfair for interactive tasks or what? Right. So fairness is definitely a good property to have. Anything else? No? Okay. So let me say a few more properties. Most of them are covered here. So one of them is a low task response time, right? You want to actually get response from as soon as you schedule something, you wanted the response to be as soon as possible. You want the high task completion throughput, like you mentioned. You need it to be power efficient, which a lot of people don't really think about, right? But then in the whole embedded world, in the automotive world, this property becomes an important property to have. Next is the lower overhead of running itself, right? You can have the best scheduler in the world, but if it takes you 10 seconds to actually make a decision, 10 seconds is an eternity in the operating system, right? Of course, 10 seconds may not be so bad if you're making a scheduler for the food delivery startup and you want to assign food to drivers, right? And 10 seconds is probably fine. But if you're giving 10 seconds to choose the next task, then that's pretty bad. Balanced CPU utilization, right? This can basically mean that you have so many cores on the system and then you have so many tasks. How do you make sure that you are work conserving in nature? How do you make sure that you are actually giving the tasks to the CPUs that are actually free and not cluttering up the CPUs? Next is fair, like you mentioned, and fair. I put a question mark here, for a specific reason, right? Because what even is fair, and even if you can achieve perfect fairness shouldn't be defined by everybody gets the same amount of time to run. It should be like how much everybody gets what they really deserve, right? That's really what fairness means, at least to me. So let's talk about this a little bit in more detail, right? So when we talk about low total response time or high throughput, how much is low and how much is really high, right? When I say I want a lower task response time, I would say I want 0, right? That's the best thing I can, but that's not possible in the real world. So you have to define boundaries on what you really define as low and high as your task response time and throughput. Next, power efficient. Now, this can be a really important property for some people, but not so of an important property for others, like for server platforms. While I would argue for servers also, it's pretty important to be energy efficient, but it's way more important to be more energy efficient on a embedded device, right? And sometimes when you're making better energy related decisions, you're probably making a scheduler run slower, or making a scheduler run lighter, or you're basically making sure that you're leaving some cores free, which will all affect your performance at the end of the day, right? Next is the lower overhead of running itself. Now, this is a pretty important one. Like I said, it needs to be pretty light to run, but at the same time, it can't be just a circular queue and then just pick the next task and runs. That's a pretty light scheduler, but it's a pretty bad scheduler. So you need to find a balance between what's the good scheduler and what's a light scheduler. And balance CPU utilization, like I mentioned, like you have to spread tasks among many different CPUs. And if you do that, then good, you're getting better throughput. But then there are advantages to not doing that also. There are advantages to packing more also. And those advantages can come in terms of energy efficiency. Those advantages can also come from the energy that you saved by power gating those cores, and you can redirect all that power to boost frequency for the other cores, right? So it's not these properties are kind of intertwined with each other. And that's the point that I'm kind of trying to make. Of course, fairness is CPU bound versus IO bound, plus what kind of tasks do we really have to prioritize more and stuff like that. So I really like this slide. This kind of encapsulates everything that I'm saying in the past 5 minutes in one neat little bundle. All the scheduler has to do is that there is no magic bullet. There is no one single solution out there. It's a game of managing what you want in terms of priorities and making difficult trade-offs, right? And this is the whole name of the game of the Linux scheduler. Let's start with the O of N scheduler. This is not the first scheduler that Linux came up with. The scheduler before this was just a circular queue and basically just pick the next task to run all of that. And that is not worth a discussion at this point because I have a lot more to cover. But so this is the first one for all sakes and purposes, the O of N scheduler. This was introduced in 2.4, I believe, yeah, and the core idea is that you iterate over every single task whenever you have a scheduling tick to choose the next task, and choosing the next task is done based on one element or one property called as goodness. Now, goodness is basically coming from 3 different sub properties, kind of a thing. One is that it comes from the property of nice. Which is essentially a weight which you are going to say that, okay, if I'm a nice task, then I can wait for some time. But if I'm a not so nice task, I want it immediately, right? So that sort of weightedness can come, or priorities can be introduced this way. Second thing is that the time slice that was unused before. For example, if your task, you had some time slice allocated to it. Now, if it doesn't use a portion of it, the half of the unused portion can be also added in the goodness property as an additional weight because you've been actually good to the scheduler, right? So you're going to get more time to run. Of course, there are also properties for RT, which is the real-time properties, and all it does for real-timeness is basically it bumps the priority up by 1,000. It just gives it a slightly absurd enough number, just so that it knows that okay, fine, and now it can basically prioritize this much more. So advantages are pretty obvious. It's a very simple scheduler to make and run. If you look at the code, it's not more than a few hundred lines, and it's very easy to read, very easy to modify, and very easy to understand. The bad part is that at every scheduling tick, whenever it has to pick a new task, it has to look for the tasks, it should look for all the tasks, and essentially it's an O of n problem now, right? And because it's an O of n problem, if it will scale really badly based on the number of total tasks in the system that we have now. The second bad part is also that it has only one global queue. Now, why is that a problem? While when you have just one global queue and you have multiple CPUs, spreading this task across multiple CPUs, while it's an easy thing because now you have to look at only one place. But the bad part is all the CPUs also will be looking at this one place. And because they're all looking at this one place, they're going to be synchronizing this one place, and they're going to lock this one place. And that's going to scale extremely poorly. So that's the O of n scheduler in a very simple, small nutshell. Let's get to what they did in Linux 2.4 right after that, which is called the O of 1 scheduler, right? The natural progression of designing algorithms. So the O of 1 scheduler, the core idea here is that it has two lists of sorts, the active list and the expired list. Each list is basically a bitmap of like 140 priorities. And the priorities are, I think, so 0 to 99 are given explicitly for RT tasks or kernel tasks, and 100 to 139 is all user tasks. And these are the priorities that can actually be changed with the nice system call, the nice that we had actually spoken about earlier. So, and basically every bitmap entry is now linked to another FIFO queue, and the tasks are picked from that FIFO queue as and when they can come, right? Basically, the whole idea is that you want to pick the task that has the lowest priority, and you want to make that run earliest, and then you have a FIFO queue for that. And then once that FIFO queue is empty, you basically go to the next priority, and next priority. Now you'll say that, hey, going to each priority is an O of n task, right? How do you find the next? What if the first priority is 140, right? Then it's a O of n finding problem. But it's not really. The architecture gives you a very nice, clean semantic called find first set, or find first set bit, or something like that. Basically, the whole job of this is to look at an entire bitmap and tell you immediately in O of 1 time that, hey, this is the bit that is set. It also has many different analogous functions like find first unset, or set first unset, and stuff like that. But this is the one that it kind of uses to give you the first priority in O of 1. Now let's look at this in a little bit more detail. Like I said, so the whole name of the game is to make sure that the lowest priority is the one. And the name of the game is to make sure that you get the highest amount of time slice based on that, right? So time slices are chosen based on two major properties. One is the static priority, and the second is a dynamic priority. Now, static priority is pretty obvious. The whole idea behind static priority is the whole priority system I spoke about, 0 to 99 for RT and kernel tasks, and the rest for the user space tasks. And based on that, there's a formulation on how the quantum is going to be designed. There's also dynamic priorities for this. Now, the whole job of dynamic priorities is basically it uses a part of the static priorities, first of all. And the second is it uses the average sleep time. Now, the idea is that if you're having a CPU-bound task, your average sleep time will be so much lesser because your CPU your task will keep asking for more CPUs, and you won't really go into that sleeping state on your of your task, right? But if it's an IO-bound task, you're likely that you're going to go to sleep. You're going to basically tell the CPU that, hey, I want to run for this much amount of time, and then I want to push this data to the disk, for example, right? And that all that disk time is basically, it has nothing to do. It has to kind of go to sleep, right? And then when it comes back, and only then it kind of gets to run. So it displays bursty behavior, and therefore it has a higher average sleep time. So this is how it basically calculates dynamic, priorities, and based on these priorities, the time slices are decided. Now, once it actually executes from one of the priority and the FIFO task is kind of empty, what it does is as soon as it finishes the first task, it basically puts it into puts it into the expired list and just gets rid of that and moves the head pointer forward, right? So I'll get to that on why we do that in just 1 second. But the flow is that when you hit schedule, you have your first set bit, you find the bit, you execute the first task, you kind of push after you're done with that time slice, and in all intents and purposes, you may not be done with that time slice, right? You may actually want to reschedule it back, but for now you just even if it's not done, you're going to put it back to your expired list of the same priority, of course, and then you're going to pick the next task of the same queue. Once this entire queue is over, then you're going to pick the next priority, right? So that's the basics of how the OF1 scheduler really works. So I have a question now, which I said I will be answering, but I'll ask you first. So why 2 priority arrays? Absolutely. So you're referring to somewhat of a starvation sort of an issue, right? So a simple example to illustrate what you just said was, say for example, you had a task here and you ran its time slice. Now it wants more time slice. So what you do is instead, say for example, instead of putting it to another queue, you just went and put it to the back of this list, right? And you just made it into a circular queue instead of a FIFO queue, for example. Now, when it does this, it goes to here, goes here, goes here, goes here, and comes back here. And say, for example, even now this is not done, and this kind of goes back to the queue and goes back to the queue and goes back to the queue. You will never really go to the sixth priority ever, right? You will eventually, but you will starve the other priorities so much so that it doesn't make sense that we are having a scheduler like that, right? So the whole idea is that's why we kind of push it to a different queue altogether. But if you attended the last scheduler class, I think you would have mentioned about aging, right? Why don't we just do aging of these priorities? Why don't, once all the tasks in that priority is done, we can just age that priority, move that priority 1 later or 2 later or whenever later, right? Why don't we do that instead? No? Okay. So the problem with aging is an O(n) operation. You have to age everything at a given point, right? When you're moving 5 to 6, you can't keep 6 as it is, because then if you move to 6, then when you move to 6, then you will also have to execute the same thing. So aging is still an O(n) operation. And what we do with having 2 arrays is basically move it to the expired list. And whenever the whole active array is empty, just swap the pointers, right? So your expired list now becomes your active list, and that's it, you're done, right? And the code for that is actually just this much. Just swaps the stuff, right? So it's a very simple way of achieving OF1ness. I don't know if that's a word, but it's a very simple way of achieving OF1 without actually going through the grueling task of actually aging something. Yes.
So the only difference between a high priority and low priority task is the time slice you assign to it, but the scheduling there's no difference in it.
So the scheduling also, so it basically will get scheduled later, right? You will pick the task with a smaller priority first.
But then once the system is running, everyone is just with the queue. Go to the end of the priorities, and then you'll start catering to the lower priority.
Yes.
So in terms of scheduling, the priorities have no differences, only the time slice you put at the end.
Yes, but they do have like, of course, once the whole thing is over, then of course, yeah, in some sense you're right, actually. That only in the first scheduling cycle they kind of have that advantage, right? But of course, these priorities can also dynamically change, like I said, because if you discover a task in the queue that is sleeping for too long, then you can basically say it's an interactive task. Let's give it a high priority. Yeah, so if it's a bursty behavior, like it sleeps for too long and comes back and sleeps for, like an IO bound task, right? Which means it kind of needs like, it doesn't need a lot of CPU time, but when it needs it, it's better to give it immediately, right? So that's kind of the idea. So any questions? Yes.
How is the dynamic? Like, how do you change priority dynamic?
I don't know exactly how this does it dynamically, but I'm guessing while making a decision, it probably when it's computing that it's already calculating the average sleep time. It already knows the sleep time, right? So it computes the average sleep time then and there, and then it bumps up the priority or bumps down the priority. That's what I'm guessing. Yeah, average sleep time is not the best metric out there, and we'll see that with the CFS scheduler as well. But the problem is with the average sleep time, it doesn't really work. The problem is because of that, the O1 scheduler guys, Ingo Molnar and all, they have added so many heuristics which are finely tunable, and which of course added a lot of overheads to the kernel. And that is primarily the reason why O1 was actually even scrapped, right? Because it got so unwieldy with so many heuristics that people just didn't know how to actually tune the scheduler properly.
But it's still O1, like even including dynamically changing priority.
I would say amortized O1, maybe. I don't know if anybody is working on like formally verifying if it's really O1 or not, but at least in principle, yes, it is still O1, right? So, yeah. Any other questions? No. All right. So, like I said, the problems with the O1 scheduler are many actually. So there are many small heuristics that were defined. Like for example, CPU affinity, right? How do you decide which task gets placed where? We were only talking about which task gets to run, right? But CPU affinity is a heuristic that is pretty important for us. It is there in the O1 scheduler, but it starts getting pretty complicated. They have like decay rates. They have priority boosts, right? Which is different from dynamic priority, and those were done specifically to avoid some cases of starvation. That's what I had heard, but I'm not 100% sure, so don't quote me on that. But essentially, all that happened was that there were so many heuristics in the play that people were like, okay, we don't know how to tune the scheduler anymore. We don't know how to make the scheduler really, really work. So then came the whole current scheduler design, which CFS is a part of. And you're in for a surprise at the end, but CFS is at least some part of it. Then we'll talk about the sketch classes, we'll talk about sketch priorities. And the whole idea of kind of revamping this entire thing into this kind of a structure is that, hey, tasks have different priorities. Tasks want to be treated differently. One scheduler can't rule them all. And therefore, what we'll do is we'll have different scheduling classes which do things slightly differently, which will cater to tasks like that, right? For example, a real-time task can't be scheduled by an O1, right? When you need the time, you need the time then and there. And when you can't specify properties like deadline, and you can't specify properties like periods and quotas. So so one scheduler can't rule them all. So they basically came up with those scheduling classes and scheduling policies and stuff like that. Let's look at what a scheduler class really looks like, right? A scheduler class has many varied, properties or policies rather. And these different policies can control what that particular scheduler class also does, right? And each scheduler class also has a priority of its own. So there are, I think, 5 scheduler classes, if my math is not that bad. Essentially, the first top scheduler class, and I'll get to each of them in depth, but each of them have a priority of their own, and that priority actually decides what when a task comes in, if it's of that class, that will actually get to execute before everybody else. And lastly, tasks can migrate between CPUs, of course, because you're writing a modern scheduler, and tasks can also migrate between scheduling classes, except a few caveats here and there. So let's get to the first class, which is of the highest priority class, which is the sketch stop. Now, this is not usable in the user space. It's only usable in the kernel space, and it's only always used for things for maintenance purposes. Generally, if you want to do a hot plug, if you want to do an ftrace, if you kind of want to do task migration, yeah, that's the big one I missed. So if you want to do something of that sort, then this scheduler class is invoked. This is not preemptable by anybody, and this can preempt everybody. Right, so this is kind of the be all end all of scheduling classes. This is when I want it, then and there. Stop everything else, right? When you run the top command, you can basically see the task as migration / the CPU that it is currently running on. That's how you can identify whether this task of this class has been activated or not. And that's pretty much it about this class. We don't really play around with it that much. At least I haven't. But yeah, it's a pretty interesting class to know about. Yes.
But all the context of the fine. Like the processor is the OS preempting the CPU for that processor to get killed.
The process won't get killed, but it will preempt it out. So either then it can be either scheduled on another empty CPU, for example, or you can basically, it has to wait or something like that. It goes back to the run queue. Yeah, it's generally how preemption is done. But whenever somebody else calls a preempt on this, that won't be allowed. So that's the idea.
Just to confirm, like
Yes.
this type of if I'm in this class, I won't be preempted, right?
Yes, yeah, you can't be preempted, and this can preempt everybody else. Yeah. All right. So yeah. Go on.
So like if I have multiple,
Yeah.
then like what if A wants to, what if A is running, B wants to?
Interesting. I'm not 100% sure if you can run the same task thread on the same CPU. Like you can run multiple task threads on multiple different CPUs, but on the same CPU, I'm not 100% sure whether you can run this. Right. For example, like if you want to do a hot plug, for example, like I think these also have like some priorities. Like you shouldn't be able to do an F trace when you're doing a hot plug, right? For example, right? It doesn't make sense. I'm not 100% sure. I've not looked at this code very deeply, but I'm pretty sure that like there is some sort of semblance of priority that hot plug should kind of take over everybody else and stuff like that. Okay. Anything else? All right, let's move to the next class. This is the deadlines class. And a fun fact about this took about 9 versions and about 4 years. Yeah, it took about 4 years to actually get merged into the Linux kernel. And that should just tell you that you should be patient, and things do happen sometimes, and sometimes they don't. So, but the whole idea of the deadline class is that it's kind of based on the earliest deadline first scheduling algorithm. It's made for tasks that are not real time, but sort of real time. What I mean by that is if you have like multimedia tasks, if you have like tasks from control systems, like if you have like a if running a manufacturing unit, and while you don't want that control system to have a pure RT real-time behavior, but you still want it to have some sort of guarantees, this is the class that you would rather want to use. It has 3 major properties. It has a period, it has a runtime, and it has a deadline. Now, a period basically tells you that, hey, this is the cycle in which you're kind of going to run. A runtime is going to tell you, say, that this is the X amount of time that I want to actually run for. And the deadline is going to tell you that this is the maximum amount of time that you should be running for. A simple example for this is that, say, for example, you have like, your runtime is set to 10 milliseconds, your period is set to 30 milliseconds, which means that every 30 milliseconds, you can kind of run for only 10 milliseconds. And the deadline, 20 milliseconds, means that while you can run for only 10 milliseconds, at max, if you have to overrun, you can overrun up to only 20 milliseconds. And that's the deadline guarantee that that this kind of class kind of gives you, right? So that's pretty much it about this class. Of course, yeah, there's an admission control strategy here. So on a normally loaded system, and if you have like a good enough admission control, this works fine. On an overloaded system, these whole deadline guarantees of you getting 20 milliseconds in this case, all bets are off, right? Because then other tasks will be contending for you, and then they will be given priority because they hadn't had a chance to run yet, right? So on an overloaded system, all bets are off, and you may not get 20 milliseconds, but the 10 milliseconds is something that you can count on that you will get, right? So that's basically about it about this class. RT is, I don't have a lot of information about RT, but the whole idea behind RT is that you want things to run in real time, and how they do it is by using static priorities. And they have like 2 classes, two policies with that, which is sched round robin, and then sched FIFO. Both these policies have the same priority itself. So when you run a task, whether it's from sched FIFO or sched round robin, regardless, it's they have an equal opportunity to be picked. That's definitely true, and its implementation is rather pretty simple as well. It's like a simple priority based doubly linked list, and then tasks are just picked from that. If it's a FIFO, it just picks from a FIFO side, and if it's a round robin, just if it's doubly linked list, then it just links it up. right? So that's pretty much that. And use cases, for RT are, your traders, your automotive, your spaces, and anything that where you have to have a very strict deadline, and when you wanted that sort of a thing, right? But this is not really good for everything else. This is not good for your laptop. This is not good for your servers. This is not great for a lot of common day use cases, because while it sounds like, okay, give me something when I absolutely want it, while it sounds great, in reality, you kind of want to make sure that all the tasks on your system are kind of, being on good terms with each other, and kind of getting them to run as they wanted to, and not being, overly aggressive by preempting everybody and then getting preempted and so that sort of a thing. Yes. Yes. Yeah, the quanta is in terms of, especially the CFS scheduler, I'll get to it. Basically, it's all nanoseconds.
Is there a reason why that's a more appropriate thing than? Because I would imagine in a faster processor, 20 milliseconds should be 10 milliseconds, right? And I wouldn't want to for who is changing.
So what do you mean for faster processor? 10-20 milliseconds should be?
Task is counted in terms of how many CPU cycles it run and not how much time.
Right, of course.
So that's why it's a bit surprising that deadlines, etc., are mentioned in terms of time directly, or maybe the OS converts it to CPU cycle.
I'm not 100% sure on is it easier to know CPU cycles?
No, it's easier for me to specify. But
is it easier for the operating system to know, or the hardware to kind of tell you CPU cycles upfront? Because we do have high resolution timers, and we have kind of gotten really good at that. But I'm not 100% sure if we can kind of get CPU cycles that accurately.
No, I think we can get CPU cycles.
We can, and with that much level of atomicity, I don't really know the real answer to this.
Because the task quantum of work CPU cycles,
right?
Not time.
Yeah.
Surprising that.
Sure, my question is why is it better to use CPU cycles? Because CPU cycles is very hard to reason about, right? It's hardware specific.
Yeah,
this
so
type of
as a programmer, it's hard for me to program.
Yes.
But as an OS, I should be caring more about. If I'm a faster OS, I'll probably give it 10 milliseconds. If I'm a slower OS, I'll give it 20 milliseconds. But I'm giving it equal number of CPU cycles. So although it's easier for me to specify, is that the best thing for the scheduler is something that's not.
The scheduler is essentially schedule applications. And if it's CPU cycles, it's hard for even basically the users to know how much time I should actually specify, right? For example, I'm running application for milliseconds, a millisecond scale. I actually know my application is millisecond level of scheduling. So I can pass this to the scheduler, say hey, give me a millisecond level scheduler. But I don't know how to pass the cycle accurate information.
Yeah, it makes it easier.
Yeah.
If I would have the ability to write it in CPU cycle.
So to think about this,
it's a digression.
And no, that's a good direction to have.
Yes.
Yeah, because from what I understand, I don't know what happens for classes like RT, because I know your question kind of it starts from RT, but for any other regular scheduler which has a time slice kind of a mechanism, it gives a small time slice and schedules out, slice and schedules out. I think for that scheduler it wouldn't matter, right? Because the time slices are so small.
It just can do more in that same.
It can just do more in that same time slice. So I think that's kind of the answer, but it makes sense for RT processes to somewhat. Yeah, but that's a good question. Thank you. Any other questions? No. Okay. So next, this is the promised land of CFS. Yes.
So we talk about the classes. I only can choose one class to use, right?
Yes.
Yeah.
Your task can only use one class to use, and also but they can migrate between tasks, right? So if you have a CFS task, you can put it to your deadline task, and you should just work, right? So that's there. So yeah, getting to CFS itself. So the whole core idea that CFS kind of introduces is the concept of V runtime, or rather virtual runtime. The concept of V runtime is taking the actual runtime of a task and then normalizing that with the total number of tasks on the system, right? And basically, it has kind of three policies, and I'll get into V runtime in a little bit more depth in just a second. But just to show about the policies, there are three major policies about with SCED CFS. One is the SCED normal, which is also called the SCED other, and basically almost all the tasks that you run on the system are run through this. There is a SCED batch, which is actually a very interesting policy, because this will actually help you if you have a CPU bound task, which is a batch process. You can kind of make that process not schedule out that quickly. So the time slice will be increased now, so that you can kind of run more for longer. And that it comes at the cost of interactivity, of course, because now you're not scheduling out that much more often, but it will give you better throughput if you have a batch process. And then last is SCED idle. And this is basically a very low priority class. I think it has a task weaker than -9 than 19 as well. I'll get to the nice values also by the next slide. But this is one policy that SCED idle has. It should not be confused with the SCED class idle, which we'll also talk about. And both the names kind of sound confusing, but this is a policy within CFS. Next, this is some trivia. Basically, Ingo Molnar created this in about 62 hours. He wrote like 100,000 lines of code, which is pretty much crazy. I don't know how he did that, but yeah. So you now know that scheduler writers are not normal human beings. Let's talk about V runtime, right? So V runtime is essentially a monotonically increasing counter. And the whole point of V runtime is that whenever your task runs for a certain amount of time, you increase this V runtime plus T at every scheduling tick, right? Every scheduling tick, you know that, okay, fine, that this is amount of runtime, I'll increase it with plus T. Now, when it increases with plus T, we also have not forgotten about a nice friend, right? The friend that we've been taking all along the ride from N scheduler. So we also add that weight of that niceness value. And then we basically, V runtime becomes V runtime plus equals to whatever amount of time that we run for into the weight that we have, right? And the core idea is that you pick the task with the smallest V runtime. That means that the task that has gotten the least amount of time to run yet, right? And that's the whole idea of what the CFS scheduler is. Let's see how it does it. So its basic data structure is a red-black tree. And in a very simple nutshell, what the red-black tree does is everything from the left of the node is a smaller value, and everything from the right of the node is a larger value. And in this case, the value of the nodes themselves are the V runtime values itself. So whenever whenever a task is get to run, you kind of increase the V runtime value, and essentially the node will be moving from the left to the right of the tree, and the leftmost leaf is the task that has the lowest V runtime, and that's the task that you pick, right? Some properties of the arbitrary is that everything search, insert, delete is all of log n. Finding the min V runtime is O of 1. Can anybody tell me why? You have to find the leaf node, right? You have to basically, you're at the root. You have no idea where the leaf is. Perfect. You can cache it, right? So yeah, it's a stupid question, but essentially you can cache this value and you can remember it, and every single time your leaf really changes, you can just remember it, right? So that's what makes it like min V runtime of 1, and that's how it still preserves some properties of the of 1 scheduler, but it's still not of, like it's not of 1 kind of, right? So that's basically how the scheduler works. Let me see if I've missed anything. No. So that's pretty much it, right? This is how it looks in the scheduler. This is the code. Basically, you have a task struct, and a task struct has a lot of things. So it has the stack pointer. It has which CPU it is currently running on, which CPU it was previously running on, and stuff like that. And all the other SCED classes, it has a pointer to that as well. And then it points to something called a SCED entity. Now, a SCED entity is basically it also houses some statistics like the load, and it carries statistics around the what CFS RQ it has. So again, the run queue, queue. So what tasks it has on that. So run queue will point to another structure here, which I have not pointed out for brevity. And this also has like the RB node, which is the red-black node. Now, the red-black node is a very simple structure, and I'm pretty sure in a data structures class, you guys would have implemented it as well. And it's just, the color of the tree and the color of the node, the left and the right? And they have aligning it to some long, and they say that, reduced instruction set needs it, but I don't know why. So don't ask me. But this is how it works. And this is one question that I wanted to ask. So we made it a huge gung-ho about, the OAuth1 scheduler and how it was able to use the sleep time to differentiate between interactive tasks and CPU-bound tasks and stuff like that, right? How does CFS scheduler do that? No? All right. So basically, the idea is that the whole idea of interactive processes is that you want CPU-bound tasks to run for longer, but they don't immediately need that time, and then interactive tasks kind of don't need to run for that long and need that time immediately. CFS does this inherently by design, right? The whole idea is that if it's an interactive task, you're going to run for a short amount of time. You're going to add the T, and the T that you'll be adding will be actually so much smaller than the T that a CPU-bound task would be adding. So essentially, you'll be moving from the left to the right of the tree very, very slowly, right? And compared to the CPU-bound task, which essentially means that you will get a chance to run much more quickly, or you'll get a chance to run before than the other tasks that actually, or the CPU-bound tasks that actually came, right? So that's the class. Oh, I already switched to sched idle. Sorry. So this is the sched idle class, and this is while it's the lowest priority class, it's not the least important class. So the property of this is basically that it is only picked when there is nothing to run. Like in the code, also, if you see, basically the idea is that only when you pick the next task fair, and if the P is null, if there is nothing to run, then basically just go and pick the idle class, right? But it has many properties. It has many useful properties. It can make your code go into an idle loop. It can basically invoke the idle governor. It can basically say that okay, that now that we have nothing to run, we can put it in some sort of a sleep state, or we can power gate certain amounts of cores, and that can save energy, and also like I mentioned before, can also help with performance, because now you can use that power gatedness to help redirect all that stuff to other cores, right? So it's a pretty important class. I would love to talk about it. Idle stuff is something that I was working for quite a bit at IBM. But for now, this I think is enough, right? Let's talk about beyond fairness. And this is where I need to apologize to all of you, because I told you that I'm going to tell you about the current scheduler, and I'm going to tell you about the latest and greatest and what's there in the Linux kernel. And I told you about the CFS scheduler. And while a lot of ideas are still sound, that scheduler is gone as of last month. It's been replaced by this brand new EEVDF scheduler. Not brand new, the ideas were there around 1995, but this scheduler really replaces the CFS scheduler. And it has just been merged into the Linux 6.6. So it would be a waste if I don't talk about the scheduler if I'm going to give you a current scheduler kind of class, right? So let's talk about why we even talk about beyond fairness, right? We are fair, we have everything that we want in the world, life is good, right? But the problem is that there is no way currently for CFS to express latency requirements. And that is a pretty big deal, because your bursty tasks require amount of time to run, but they require them immediately. But your other tasks, they can take their time to run. CFS only specifies or rather controls the amount of time you can run for, but it doesn't tell you when you can run that for, right? And that's a pretty big problem. There was and niceness kind of only gives you the amount of time you can run for. So there was these guys who came up with this feature called latency nice, right? If you can say this is when you give me this much amount of time, you can also say give it to me now, right? So there was a feature called latency nice that was introduced, which was actually worked by a very close friend of mine who's sitting across the desk from me at IBM, Parth Shah, so shout out to him. He was working on it for many years, and a lot of these ideas are kind of now translated into this new EEVDF scheduler. Now, the whole idea of the thing is you want to deal with latency sensitive tasks while also not losing like the properties of the CFS scheduler. Yeah. Yeah.
Is it that the time you get to execute is impacted by all the other processes running? You can't guarantee.
Yeah, you can't just guarantee. You can kind of only guarantee that okay, this is the amount. If you're a less nice task, for example, that means you kind of need more time to run. But you can't say, okay, if I'm a less nice task, I need to run now, or I need to run quickly.
You can't change.
You can change the niceness value, but the changing the niceness value won't affect how quickly you can run or when you can run.
Not by as much as I.
Yeah, not by as much. Like it's not like it's kind of as a consequence, but not as a direct byproduct. Like it's somewhat of a byproduct, but not as a direct consequence. Yeah, that's why like the whole latency nice was kind of introduced to kind of just say that, okay, fine, I have a new value. Now you look at this value also, and now you say, okay, if I'm lesser latency nice, then give it to me to run now, right? So that's the problem with this problem with CFS. There are many other problems as well. Like over time, it has also gotten a lot of heuristics, and I've not covered about any heuristics, unfortunately. But it has a lot of heuristics, and it can get pretty complicated and unwieldy to manage again, right? So this time, Peter Zylstra, with again, I think Ingo Molnar also was there. These guys kind of figured it out, and they kind of wrote a completely new scheduler for solving this problem. Now, let's talk about this whole new scheduler. It's called earliest eligible virtual deadline first, right? It's a mouthful. And the whole problem is that, like I said, like, CFS kind of only has one knob, which is nice. It'd be nicer to have another knob. And so what EEVDF does kind of is it has two parameters again. It has our good old friend nice again, which is again picked up from the whole history. And the second thing it has is something called as the request size or the slice length. Now, this is something that is used to compute the virtual deadline. Now, we spoke about deadlines, but we don't know what a virtual deadline is, right? So virtual deadline is basically the earliest by which a process should have received its CPU time, right? So now you're kind of giving a close boundedness to that, okay, hey, this is the closest by which that my next process should be on, right? And the basic logic of how to calculate that information is basically by saying, no, the virtual deadline is equal to VEI. VEI is basically your V runtime. So we still have the concepts of V runtime. We have R of I, which is the request time or the base slice, which is I think 3 milliseconds in the Linux kernel as of today, but this is tunable in the user space, right? So from this interface. And the W of I is the weight, like we said, which is dependent on the nice value. Right? The whole core idea is that smaller slice you have, the earlier the deadline will be, and therefore you can now control when this new task will come, along with how much time you can run it for, right? So that's the core idea of it, but it also adds a few more things on from the EVDF side of things. It adds something called as lag. Now, this is not a EVDF specific idea. It can be implemented in CFS. But the problem that CFS also faced was the fact that a process may sometimes get more CPU cycles, or sometimes it can get less CPU cycles, and for reasons beyond its control. It can be because of its waiting for I/O, it can be because of context switch overheads, it can be because of scheduler overheads itself, right? And there is a very, very small duration beyond which it can sometimes get its time, and sometimes even the task which actually is supposed to get 10 milliseconds doesn't get it, right? And how they kind of do that, or how they kind of mitigate that, is by introducing something called as average V runtime. Now, average V runtime until now was a pretty had not been implemented in the Linux kernel because of how computationally expensive it was. I don't know exactly how they've pulled it off, but essentially what they were using instead of average V runtime is min V runtime. So folks who have been taking the 4-credit course, they would have probably read the scheduling bugs paper, or the decade of wasted course paper, if you guys have read it, or if you're supposed to be reading it. There's a case study on like how the min or the min V runtime kind of affects this problem, and they kind of said that okay, min V runtime is bad, and you just use max V runtime, right? So but this kind of also introduces average V runtime in the game, and essentially the whole gung-ho about all of this is now that processes will get a quicker time to run. And and the thing is that okay, yeah, so the thing is also that and the thing is also that that while it will only affect when we can run it, but it will not affect for how much we can run it. For that, you still have to use the regular nice parameter, right? So that's about all I had for scheduling in Linux. And are there any questions up till now before we get into the boring stuff? Yes. So, okay, so the thing is, when you want to calculate like the entity lag, you're kind of saying that, okay, fine, we want s minus s of I, or you basically want to calculate for every single process, right? So it's like an I thing. Like you want to have a summation of sorts, right? So an average of V runtime will kind of give you that inherently. Yes.
Is there something specific that triggered change from CFS to TP?
That's a good question. So
What changed?
from my understanding is, so latency nice has been proposed almost every year at the LPC and conferences like that. And every year it used to be shot down because they just couldn't agree on the right interfaces and stuff like that. This year, I think when it was reintroduced again, something snapped for Peter Zylstra, and he just said, "Probably I'll just write a new schedule."
Telling about it.
Okay, so there are two major use cases, and there are two major companies are kind of promoting it. I think many more as well, but ARM has been a big proponent of latency nice. I think it's really useful for their mobile-based devices to kind of have a sense of running things faster when they want to run it rather than running them for longer, because I'm guessing like a bursty nature of tasks is so much more common for like mobile-based workloads than anybody else. We at IBM also had a use case. That's why the patches that were being reposted were my friend's patches itself again and again. And servers also have a lot of burstiness in terms of workloads. It depends again the kind of server workload that you're running on, but we had a use case for that. Burstiness is essentially the answer for this. Yeah. Any other questions?
I have a question.
Yes.
So, like, do you know how do they evaluate, like, whether the performance of like the new schedulers, because they are going to be facing this problem?
Right.
How do you convince people that like, hey, this eVDF is going to like perform better than CFS?
So from what I've seen is, so when Peter Z he pushed these patches on the mailing lists, people from all across the companies, they basically started running their workloads on it and then reporting regressions or improvements. Right. That's basically how I've seen it. There is no formal way of verifying it. People did see regressions for a lot of workloads as well, but I'm guessing like all of these will be eventually ironed out, and all of them are already ironed out when they've been put in the 6.6. But even if the ones that are newly discovered will be eventually ironed out, I'm guessing like folks like Ingo Molnar and Peter Zylstra, people like they don't look at them with that much amount of skepticism because they have themselves extensively tested these by themselves. So
in terms of results, like how much faster it is compared with CFS? Like, what's actually the biggest change in terms of numbers?
So I think it's marginally faster. It's not any large by a large number, but I think the main thing that they're kind of pitching with this is the control for latency sensitive processes, right? Because if they just cared about latency sensitive processes, they would have just pulled latency nice and they would have called it a day. But the whole point of making a new scheduler is to simplify the current problems. And because you will eventually keep building upon the scheduler and there is no way around it, right? And it's better to build it on a simpler design, which inherently incorporates the semantics rather than just putting patchwork, which will eventually happen with the schedule, I'm sure.
Other questions?
Questions? No. Yes.
So CFS lets you run for a longer period of time, but not quicker.
Yeah.
How soon it is next?
Yes. Yeah, that's the problem. Okay. Oh, you have a question? Okay. Do you have a question? Okay. Yes. So I would, I don't know actually. So I would currently say that use the CFS as it is. Again, it depends on what your desktop usage is. If you want to mine bitcoins, I don't know what to do. But I think using just the regular CFS is fine. I did see some regressions very recently on some gaming benchmarks. So I don't know if you're a gamer, but it kind of, I don't, they'll be eventually ironed out. I'm not sure why those regressions are even in the first place. I don't know that. But I mean, eventually everything is going to go to EVDF. So it's probably good to just switch to that. But that's not going to be like too soon, right? Because these are LTS kernels that have been supported for a long time. So CFS is going to stay for the foreseeable future. Now in the newer kernels, they only have this new schedule, unless you backport the patches to RHEL and all that. I don't know.
Otherwise, you just like CFS.
Yeah, so it is replace CFS. There's no CFS anymore in the new kernel. So when you do a schedule call the schedule function, it goes into this.
Oh, but I can make use of the latency features only if I choose, not like I coded a function, coded a program.
Yeah, by default it will run with the weights that it by default usually runs, right? Which is true for even CFS, right? If you don't play around with the weights, even everything is still kind of fair. Right. There are heuristics that automatically identify and kind of give it, more or less time, but yeah, that's a different discussion.
More questions?
Yes.
Before this slide, after this slide, things won't be on the exams, but
Okay.
at this slide right now, things will be on the exams. So it's better to ask a lot of questions.
Okay.
Make sure we understand the schedule.
But
CFS weights, does the CFS provide sort of guarantee that it's maximum fair between the
theoretically, yes. But in reality, it depends. And why I say that it depends is because it has heuristics that do identify behavior of tasks. And based on that, it could play around with priority posting. So for example, let's say you have an interactive task and you have a CPU bound task. Even if you don't explicitly state it, I think CFS does have some sort of metrics to do that. And even beyond that, if you have, say, for example, some sort of load balancing options, or if you have like CPU affinity options, I think the CFS can identify your affinity to a particular core and kind of make sure you schedule on that. And for that, it can kind of introduce unfairness, for the lack of a better word. Okay. Yes, go ahead.
Can you explain that first bullet point, how the latency sensitive processes naturally get a quicker time to run?
Sure, yeah. So the whole point about latency sensitive tasks getting like a more quicker time to run is by now introducing this whole concept of deadlines, right? And the whole idea is that, hey, if we have like a smaller slice, like for example, if you look at this virtual deadline function, basically what it says is that, okay, fine, now we are going to say that this is the earliest time by which you should receive the next, by which your process should receive CPU time for, right? So we're introducing this new metric, and we're calculating this virtual deadline by using this whole request slice length, and we're saying that, okay, when we have a smaller time slice, or when a smaller time slice is set, for sure that this is how soon your next task should actually be scheduled for. Right? Yes.
I think the earliest time by which the process should have received, but doesn't that mean that you're limiting how early you can start? Shouldn't be the latest time by which it could start, so you have guaranteed that it'll run at that time. You're basically guaranteeing that it'll run at a certain time with the deadline. Or is it saying that
No, I think this is kind of so it's not a guarantee per se, but it's kind of a more of a recommendation that yes, this is something that should happen. I'm not 100% sure. I think it's a good question that does it really guarantee by this time or not? I really don't know, but I think this is just a metric to say that if there's nothing, again, I don't know what happens on an overloaded system. This would all bets maybe off, but you again don't know because this may have took care of it, right? But I think I see your point. Yeah.
It's just like an estimate.
It's a estimate. It's a good estimate, but it's still an estimate. Yes.
Just going back to, I think they're talking about the use of the word earliest versus latest. So let's say you calculate your deadline to be 20 nanoseconds. You can get scheduled before that. It's just that 20 seconds like your ideal deadline. So I think they're just saying instead of earliest, it should say ideal latest. It's just in the use of the word.
Yeah, I do agree with you. Yeah, I don't know if I'd use the word ideal latest. Ideal would be
Recommend.
it's very loaded. Yeah, that's about it. Any other questions? Yes.
Are the tasks, is it preemptive scheduling or?
Yeah, this is preemptive scheduling. All of this is preemptive scheduling. Yeah. It really builds upon the ideas of CFS, right? So it doesn't get rid of the whole virtual runtime concept. It doesn't get rid of the arbitraries. And all of those ideas are still there. Okay. Guessing no other questions. So let's talk about my work. And for my work, I kind of also need to give you a little bit more background. So more teaching about how C groups work. So the whole idea is that the whole cloud infrastructure, everything from Docker's, containerization, Kubernetes, the whole thing is built upon like container primitives, which are known in terms of C groups, namespaces, unified file systems. And while I'm not going to talk about all of those things in depth, and that's another class in itself, I will introduce C groups to you because that's kind of important for our project, right? C groups is basically a mechanism that can account and limit resources for a particular task, right? And there are many kinds of these C groups, and there are C groups for CPU sets, CPUs, memories, networks, block IO, and all of these limit different kinds of resources, and of course account for different kinds of resources as well. The way C group is kind of designed is in a hierarchy way, where you can have multiple processes kind of inherit properties from parents, and that kind of gives it I wouldn't say like a forking kind of a model, but it's kind of similar if you want an analogy, right? And of course, there were two versions of it because we can't get anything right in version 1. And V1 basically was a pure hierarchical model where there were like, say all the C groups had like multiple different virtual folders, and every single task, if you wanted to be say limited by the CPU set, and if you wanted it to be limited by memory, you needed to put the PID in both this folder and that folder. And that caused many problems. I won't get into those, but now it's like a flat hierarchy where you can kind of there's a controllers file, and then you can just say plus memory and plus you can just append what kind of controllers you want to this, right? So this is the basics of what the C groups really is. I'll talk about the CPU controllers because the title of the slide was for CPU. And there are two CPU controllers. One is the CPU set controller, and the second is the CPU bandwidth controller, also known as the CPU controller. The CPU set controller is a very simple idea where we say that, okay, we want to pin a certain number of tasks to a certain number of CPUs, and that's it. We want to call it a day, right? And this is very useful for a lot of use cases. If you want like pure performance isolation, if you don't want effects of NUMA to trouble you, right? And a lot of people are actually using this. I think I also mentioned some HPC workloads and some web servers when you don't want them to interfere with each other, right? So the whole idea is that it's a very easy way to kind of isolate your performance and kind of get a CPU isolation. The problem is most cloud providers, like who are like multi-tenant cloud providers, they don't really use this, right? And they can't because if you have like 100 clients, you can't just say, okay, you take one CPU, you take one CPU, and I'll just call it a day, right? You have to kind of share CPUs among processes, and that's how a regular scheduler would also do. You have to kind of treat them as process groups rather than just companies, and then every company gets one CPU, and then that will eventually turn into every company gets one data center of its own and call it a day, right? But so that destroys the whole cloud model. So the whole cloud so the CPU bandwidth C group controller is kind of introduced, and it has two major properties. It has a period and it is a quota. Yes.
Are we talking about AWS kind of cloud?
Yeah. AWS.
Again, specified period and the code.
It depends. So, okay, AWS has many offerings, first of all. I'm talking about an offering where you say, okay, I have a Docker container, for example, right? I want to run this Docker container, get my results. What does your AWS do? Does it still spawn a VM? Serverless could be one use case for it, right? Even for your VM, for example, let's see, the whole point of actually spawning a VM was introduced because containers are not that secure. That's a different problem of its own, right? But then even if they are secure, I think even on a VM, if you're running, there has to be some sort of scheduling, but then it won't use this sort of a bandwidth scheduler, right? But I think serverless is probably one of the bigger, one of the use cases. But I'm sure that you should be only able to spawn, yeah. Yeah, microservices I think is a good use case.
Yeah, as in whatever AWS manages it, then it's.
Yeah.
You run it, I'll run it for you.
Yeah, I'm sure you can just get services where you can just spawn containers out of the blue, right? Which was the dream of the containers to begin with, but yeah. So this is the more common use case, and the whole point on how it works is it has like two major parameters: a period and a quota. And the period essentially means that, okay, this is the amount of cycle or the amount of time that that is there in your cycle, and the quota is that the total amount of time that you can run within that period. So if you have like 20 milliseconds and 100 milliseconds, you're going to basically say that, okay, I know after if I utilize more than 20 milliseconds, then kick me out, right? And this is a very easy user space mechanism to kind of control how much a user can get to run. So your AWSs can very easily kind of say that, okay, you're paying for 20 milliseconds, you're paying for 0.2 vCPUs. I'm going to cut you off at that, right? I'm not going to give you 0.5 vCPUs even if I have the time. You pay me more. So that's basically how C groups work. And how it works in terms of the container side of the world, in both in terms of Docker and Kubernetes, what they do is they don't really care too much about this period and quota. Because applications don't, right? Applications, you're not going to ever find somebody who's going to say, okay, hey, give me 10 milliseconds of runtime. Nobody's going to tell you that. People are going to tell you, okay, fine, give me 2 cores worth of runtime. Give me 2 vCPUs, right? vCPUs is a very popularized term. Kubernetes has also popularized the term millicores or microcores, no, milli CPUs. Yeah, milli cores and milli CPUs, right? And all of these guys, what they do is, because they still want to use the benefits of the bandwidth controller, they kind of have a conversion between milli CPUs and period quota. Now, the way they convert it is they keep the period as constant, which is the 100 milliseconds. It's been set like 12 years ago and never changed after that. And it's a user space tunable value, so it should be changed, but it's not changed. And the quota is the one that has been changed across the platform. So if you ask for like 0.5 vCPUs, essentially what it's going to give you is going to give you 50 milliseconds of quota within 100 milliseconds of runtime, right? And that's kind of where the problem also stems from, because if it's really dealing with ratios, what is stopping it from making it 5:10? What is stopping it from making it 500:1000? I can't do math, but if you're only dealing with ratios and you're not dealing with the actual tunable parameters, then there is nothing stopping you from from knowing what is right. And it's not really the Kubernetes fault. It's not really the containerization fault, because they don't really know what the period should be, because they don't know the application, what they're running, and they don't know the periodicity of that application, right? And it's very hard to know this periodicity of the application in user space as well. So what do Kubernetes do? So Kubernetes also kind of, wherever you kind of spawn a workload, like Chirag also said, you can kind of say that I want, 0.5 vCPUs, I want 1 CPU. And it'll basically spawn a VM for you, it'll spawn something for you along those lines. And it's, in this case, let's assume that it spawns a container and you're going to run a task. Now, the thing is, as a user, it's 1 CPU, 1 vCPU is 1 CPU worth of runtime and not 1 CPU itself. So you can sometimes get it wrong. So what you do is you basically tell AWS, hey, I don't know what to set my vCPUs. This is something that I'm roughly setting it for you. You auto scale it to whatever you want. I will pay you for your trouble, right? And basically what these guys do is they're going to say, okay, fine. We have many autoscalers out there in the world. We have like machine learning autoscalers, we have rule-based, we have statistical analysis, we have everything, right? And based on your workload behavior, we are going to set the new vCPU or the new milli CPU. The problem with all of this rounds back to they only tune the quota and never the period, right? And the question that I kind of thought of, or that came to my mind, is what is the advantage or disadvantage of keeping a 100 millisecond period all the time? because applications are different, applications behave differently. So shouldn't that period be, or a period and quota rather, shouldn't that be according to the way they actually behave, right? Because this ends up over allocating so many more resources, and it also ends up not giving that much better of a performance to begin with. So that was the kind of question that we set out to answer. And basically what we got to is that we need a better CPU, better solution that is fast, because we can make at a millisecond granularity, because workloads are that frequently changing, and the whole machine learning workloads and all that, they actually sometimes even take like 48 hours worth of data, and then they make a decision and stuff like that, right? So you need something that is fast, right? You don't need something that's slow. Second thing, that is non-disruptive. Like a lot of these containerized solutions like Kubernetes Autoscaler will actually restart your pod, and only then will apply these new changes. I don't know why it needs to do that, because it can hook into the C group interface directly, but it apparently restarts your pod, right? For whatever reason. It has to, so our solution has to be non-disruptive. And the third, it has to be accurate, right? You can throw all the complicated algorithms in the world, but if you're not applying all your algorithms on the right heuristics, then you're probably not getting the right data. Right, and so we should be able to trace this correctly, and we should be able to get better CPU utilization statistics. And I think I'm out of time, so I will stop here if you are.
So do you have the event like to go?
No, it's fine. I can skip that. Yeah, it's fine.
So I guess like many of the folks have to leave.
Okay.
So if you have like kind of for 1 or 2 minutes, like just to go over like the basic ideas.
Okay, yeah, I'll just take 1 minute or 2 more minutes of your time, right? The whole idea is that we want to do runtime tracing, and we want to do this in the operating system, right? And runtime tracing is in the operating systems is not easy, because you're context switching all the time, and you expect your runtime to be like this, but it's really like that. And then there are really just two approaches of how to, or there are many approaches. I'm probably stupid, I didn't know of any better. The two approaches are, one is you do like a period bound runtime tracing, where we basically say, okay, within like 100 millisecond period, I'm going to take like a summation of all the times that I've run, and I'm going to kind of get that number as my new runtime and yield time. Right, but the other way, and this is what that is. So in this case, 100 milliseconds, so it's run for 70 milliseconds, and you're idle for 30 milliseconds, even though you have like gaps in your code, right? So that's one way. Another way, but then that's kind of bad. Especially because if you have like, say if your behavior is like 30, 40, 30, and then if you have like 100 milliseconds, and then the first time we'll say that your runtime is 70 milliseconds, the second time we'll say it's 50 milliseconds, the third time it's for 60 milliseconds. And then now what do you set your period and quota to, right? What do you set your entitlement to? You can take an average, but that's not great, right? You'll be bad for 99%. So, and that's a problem. And how we kind of solve it is we basically do period agnostic runtime tracing. And the way we do it is we set up like time clocks. We call it yield time and accumulated time. And we basically find out how long an application is yielded for. And if that application is yielded for long enough or more than its bandwidth slice, then we know for a fact that that was actually the sleep time. And then we take the accumulated runtime, and then we kind of find the difference of that. And I'm probably explaining it terribly here, but the idea is that if we can kind of get beyond the shackles of whatever the scheduler gives us, which is 100 milliseconds, or even if we can set up some other number, if we can go beyond that shackles of that, we can actually estimate what is the exact behavior of applications and make decisions based on that. So decision-making granularities, we pick the 99th percentile of the runtime and yield time, and we do that per run queue, and we kind of make a decision based on that. And we introduce like a new Linux interface for it, so there's accessible Y user space. And the idea is that we kind of you can enable disable tracing, or you can say, okay, automatically just tune my period quota, don't recommend anything and stuff like that. Experiment setup, I think pretty standard. So we set up where we test with the Kubernetes VPA. We also test with Docker 50 and 99 percentile, and these are kind of retrospective approaches. So these should be better, but they're not, because even though you can get to see the entire runtime of applications, you still kind of don't have everything. We show that even if you can see everything, you're still not making the right decision, even on the worst case scenario, right? So that was kind of the idea. And I think, this is like a sleeping busy micro benchmark. We show about 25% lower CPU utilization compared to Docker P99. So even in a retrospective approach, which restarts the workload, we kind of get 25% better. And this is in runtime. And for real-ish benchmarks like EPFL Cloud Suite, we see better numbers where Kubernetes actually interestingly performs much worse in a lot of cases, and we can still get better CPU utilization in terms of CPU utilization as well as throughput. Yeah, media streaming is the last one. We see 151% better performance than Kubernetes, and 25% lower, CPU utilization than Kubernetes, and 67% better than Docker and stuff like that. So that's basically what I had. And thank you. Sorry for overshooting by quite a bit.